This is a total production. Hello, Chem Minions, Surveyors. This is going to be our second practice video for Chapter 6. Here we're really looking at intermolecular forces, and we've got 4 that we need to really think about: dispersion, dipole-dipole, hydrogen bonding, and ionic. And so with these, we have to think about one individual bonds, but we also need to think about the overall structure. And so for when we look at, say, our first option here, we have sodium nitrate. All right, so this is an ionic compound, so we automatically know it has ionic bonding because you have an Na plus and you have an NO3 minus. Now, the thing with if we look at these, this is a polyatomic ion, and with it, this has covalent bonding that occurs to give us the ion. And so you have NO or N double bonded O bonds in there. So because of that, you're also going to have dipole-dipole as an option. It's nowhere near as strong as what we're going to get with the ionic case, but it definitely has dipole-dipole. And here's the caveat. Everything that has electrons, everything has dispersion. The only thing that doesn't have dispersion is H+, because all that is a proton. So these would be the 3 intermolecular forces that we would expect for an ionic compound like sodium nitrate. Okay, dispersion being our weakest, dipole-dipole being our next strongest, and then ionic being our absolutely strongest. This won't have hydrogen bonding because you don't have a hydrogen with a covalent bond attached to either oxygen, nitrogen, or fluorine. So we don't have that here. Now with Br2, all you've really got here is a bromine-bromine bond. All right, so there's no difference in electronegativity between 2 bromine atoms. So we don't have dipole-dipole, we don't have hydrogen bonding, right? And we don't have ionic. So the only thing that this guy has is dispersion. Okay. Anytime you have 2 of the same element attached, pretty much these are non-polar molecules, and all they're going to have is dispersion. Okay, so if you have, so I'm going to throw that in here too, non-polar, right? It's typically non-polar molecules are only going to have dispersion. Okay. Now we look at this guy here. This is specifically called methanol. It's not important for you to know the name just yet. Chapter 9. But for right now, this is methanol. And so what we see here is we have a bunch of CH bonds. We have a CO bond. So that bond in particular is a polar bond. And then this bond right here, O and H, that's a polar bond. So right off the bat, dispersion, anything with electrons has dispersion, so it's not necessarily important. But if we look at dipole-dipole, it has 2 polar bonds. So it definitely has dipole-dipole. So anytime you have a polar bond, right, you can think that it's going to have dipole-dipole. Now, this has the very specific dipole-dipole of hydrogen bonding because of this bond right here with the oxygen and the hydrogen, right? Anytime hydrogen has a bond with either oxygen, nitrogen, or fluorine, it's going to have hydrogen bonding. Now this doesn't have, all of these bonds are covalent. There's not a single ionic bond present, so we don't have any ionic stuff going on. Now, we look, I told you up here, this only had 2 polar bonds, right? That's because a carbon-hydrogen bond, as I have said repeatedly, is a non-polar bond. Well, look what this structure right here has. Nothing but CH bonds. Everything about this is non-polar. So every bond here is non-polar. That means the entire molecule is non-polar. So it doesn't have dipole-dipole, doesn't have hydrogen bonding, and of course it doesn't have ionic. So the only thing that this molecule right here has, which is called ethane, the only thing it has is dispersion. All right, next up, I'm going to try and leave the dispersion part in here. Next up we have NH3. This is ammonia, right, or trihydrogen nitride. So of course it has electrons, so it has dispersion. Now this has 3 NH bonds, so those are polar bonds. So this has dipole-dipole, but more importantly, it has the strongest dipole-dipole of hydrogen bonding. Remember the scenario I said? If you have a hydrogen with a covalent bond to either nitrogen, oxygen, or fluorine, it has hydrogen bonding. Now these are covalent bonds, right? They are polar, right? I'll put that. These are polar covalent bonds, but there's no ionic bonding here, so this isn't ionic. No ionic stuff going on. Next up, we have CO, so carbon monoxide. More or less, if you were to look at this, it's going to look something like that. All right, it's not pretty, but it's going to look something along those lines. And so all it really has is one polar bond. And so it's got electrons, right, because it forms bonds. So we know it has dispersion. Then we know it has dipole-dipole because the electronegativity between carbon and oxygen makes this a polar bond, so it does have the dipole-dipole. There's no hydrogen, so of course there's no hydrogen bonding. These bonds are polar covalent, so it's not ionic either. All right, so that's out. Next up, we have CO2. All right, here's the deal with CO2. If you were to look at CO2, this molecule would look something like that. Now, why is molecular geometry important? Because even though this has polar bonds, okay, what do you notice? You've got the polar bond with this guy pulling electrons out here, and then this other polar bond has the electrons moving out this way. So what happens? You have symmetry in the molecule to where these two polar bonds cancel. So this molecule is in fact non-polar. All right? Crazy. You can have polar bonds and still be a non-polar molecule. All right? So what does that mean? If this is a non-polar molecule, does it have dipole-dipole? No. So the only thing this guy has is dispersion. Yeah. Don't get lazy. Look at the structure of the molecule. All right, next up, we have this guy right here. It has 1, 2, 3 bonds where it's a carbon-hydrogen bond. And remember, each one of those are non-polar. So those don't really count in terms of, do we really care about intermolecular forces here? Because all those really give us is dispersion. But this bond here is a polar bond, right? So I'm going to put that as polar. Now, does this polar bond cancel with anything else? No. Because these are all with hydrogen, right? These are all non-polar, and there's only one polar bond. You need multiple polar bonds to cancel in order for, you would need at least a second one that is positioned 180 degrees away, like with this linear molecule here, to cancel it. There's no cancellation here. So this has dipole-dipole. Now, it does have hydrogens, but those hydrogens are bound to carbon. So it doesn't have the hydrogen bonding, and of course they're all covalent bonds, so there's no ionic intermolecular forces either. All right, next up, now we've changed it to where, look, it's got 1, 2, 3 chlorines attached. So you've got a polar bond, and a polar bond. So all three of those are polar. Now, none of them cancel because this is a tetrahedral center, right? What does that mean? That means in a tetrahedral, all those bonds are about 109 degrees away from each other. Did you hear me say 180? No, you didn't hear me say 180. That's what you would need, right? You would have to have one. Well, there's two things we got to have here. We'd have to have an even number of these polar bonds, and with them being even, they would have to completely cancel based off their bond angle. 180 is a canceling bond angle. 109 is not. Is 180 equal to 109? No, it is not. So, what does this have here? Of course, it's got dispersion because it's got electrons, but it also has dipole-dipole. It doesn't have hydrogen bonding because that hydrogen is bound to a carbon. That hydrogen is not bound to an oxygen, a nitrogen, or a fluorine, so this is all it's got. Next up, now, right, if we were to name this, this would be like carbon tetrachloride, right? You have 1, 2, 3, 4 polar bonds. Okay, but what does that mean? That means that this is a highly symmetrical molecule now. All of those polar bonds are with the exact same thing, a chlorine. And that means they all have the exact same electronegativity difference, and that means they all cancel. So this has dispersion because it's got electrons, but it does not have dipole-dipole, it does not have hydrogen bonding, and it does not have ionic. So that's all we would say for something like carbon tetrachloride. Dispersion only. All right, so hopefully this kind of highlights the importance of, it's not just the bonds that are present. You got to look at the overall structure of the molecule, look at its geometry. Can those cancel? Are those bond angles 180 degrees away from each other? If not, then you know it's polar as a molecule overall. Anyway, so from there, stay weird. I will too. Adios until next time.